I was just looking at a river map the other day, and you see that incredible branching pattern from the air, and you just think, that can't be an accident. It looks, I don't know, designed.
It really does. And your intuition there is spot on. That's our whole topic today, really. River systems aren't just a random collection of channels. They are um, deeply structured, self-organizing systems.
So for this deep dive, we're going to try and pull out the mathematical blueprints behind it all, the geometry, the physics, how rivers literally build themselves based on the material you shared.
Exactly. And to start, you have to think about scale. I mean, we're talking about everything from a tiny little rivulet up to, the Amazon basin.
Right.
The mass for that is what we call power laws. They basically show a consistent relationship between two things, like y equals k times x to some power. It means the pattern holds no matter how much you zoom in or out.
Okay, so give me a real-world river example. What are X and Y?
A classic one is Hack's law. So let's say x is the total area a river drains. Y would be the length of the main channel. The power law tells us that this relationship between length and area stays remarkably consistent across scales.
And that idea of things looking similar at different scales, that's fractal geometry, isn't it?
That's exactly where it comes in.
Yeah.
A river network is a perfect example of a fractal. It has a complexity that's somewhere between a simple one-dimensional line and a two-dimensional plane.
So it's more than a line, but it doesn't just fill up the whole map.
Precisely. Its fractal dimension reflects how efficiently it branches out to cover the area.
So we have the big picture math, but how does the river actually build that structure? I was fascinated by Horton's laws in the sources.
Ah, yes, from 1945. That's the foundation. Horton figured out the topology, the actual rules of connection. He classified streams by order and found these amazing geometric progressions.
The key number there that jumped out at me was the bifurcation ratio.
The R sub B, yeah. It's the ratio of, say, first-order streams to second-order streams. And what's wild is that it almost always falls between 3 and 5.
3 and 5, that's a really narrow range.
It is. It points to a kind of universal principle of efficiency. And here's the kicker. That cosmological ratio, that number, it mathematically determines the fractal dimension of the whole network we just talked about.
Wow. So the way it connects dictates the shape it takes.
The topology constrains the geometry. It's all one beautiful, unified system.
Uncovering these kinds of deep hidden patterns requires some pretty advanced tools. We really want to thank our sponsor for helping us make these deep dives possible. This is all sponsored by Embersilk. If you need help with AI training, automation, software development, or even just figuring out where AI agents could make the biggest impact for you or your business, check them out at embersilk.com.
So we're back. We have this mathematical blueprint, but what's the actual force on the ground that's, carving the landscape according to these rules? It all comes down to energy. The river is constantly trying to balance its energy budget. The key concept is stream power, which is basically the rate at which the river dissipates potential energy.
Through erosion and moving sediment around.
Exactly. The channel adjusts its width, its depth, its speed, all to stabilize its power output along its length. It's this constant dance between the water's power and the sediment it has to carry. It's natural engineering.
But there was a finding in the sources that seemed to break that rule, right? Something about the headwaters, the very smallest streams.
Yes, this is so interesting. While big rivers follow that nice scale-free power law for their width, headwater streams, they don't. They follow what's called a log-normal distribution.
And what does that mean, practically speaking?
It means they have a preferred size. Unlike the power law where anything is possible, there's a characteristic width that is most common. And it turns out to be about 32 centimeters, plus or minus 7.
32 centimeters, that's incredibly specific, and it holds up everywhere.
It's remarkably stable across different climates and landscapes. At that very small scale, simple physics things like soil strength or the way plant roots hold a bank together imposes a size limit. It's a fantastic example of a physical constraint overriding a purely mathematical scaling law.
It's amazing. And understanding all of this, from the big fractal patterns down to the specific width of a tiny stream, that has huge implications for river restoration, doesn't it?
It's everything. If you want to build a stable, healthy channel, you have to work with the river's natural tendencies, with its math. You can't fight it.
So the big takeaway is that this beautiful complexity we see is really just the result of simple physics trying to find the most efficient way to do its job.
That's the perfect way to put it.
But the idea that really captured my imagination was taking this math off-planet. The sources suggest using these same principles to analyze river-like networks we see on Mars or on Titan.
It's the next frontier. Imagine using the fundamental rules of Earth's rivers to figure out the history of water on another world.
What an incredible thought. Well, if you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.